students. Today we are going to see about how to write the Vhdl program for 4-bit binary adder subtractor in structural model. This is the Vhdl code for 4-bit adder subtractor in structural model. This is the block diagram for 4-bit adder subtractor. Here we have 4 full adders and 4 XOR gates. Okay. In structural model, we have to define Vhdl code for XOR gate and full adder. So first we see the Vhdl program for full adder. Okay. In this program, full adder is the entity name, BHV is the architecture name. Okay. In every Vhdl program, we have entity, architecture and library part. In C programming, we include header files on the top side. Here we include library. Okay. In entity part, first line is entity, entity name is. In this program, full adder is the entity name. So, entity full adder is. Next, I am declaring input output ports of the full adder. All of you know that for full adder there are 3 inputs and 2 outputs, sum and carry or outputs. Okay. X, Y and Z are inputs. All are single bit value. So X, Y, Z colon. You have to use mode in. Then all are single bit value, so STD logic or you can use bit. Okay. Next, sum and carry or output. So sum, carry colon, you have to use mode out. Sum and carry or single bit value, so STD logic. STD logic or you can use bit. Okay. Next, in the third line, you have to write end entity name. Full adder is the entity name, so end full adder. Okay. Next, architecture part. In the architecture part, first line is architecture name of entity name is. Okay. In this program, as I told you, full adder is the entity name, BHV is the architecture name. So architecture BHV of full adder is. Next, you have to use begin. Okay. Next, I am defining the logic of the full adder. Okay. All of you know that sum is equal to X XOR Y XOR Z. So sum less than equal to X XOR Y XOR Z. Okay. Carry is equal to XY plus YZ plus ZX. So carry less than equal to X and Y or Y and Z or Z and X. Okay. Dot is replaced by logical and. Okay. Plus is replaced by or. Next, I am closing architecture. So end architecture name. Architecture name is BHV. So end BHV. Okay. Next, I am writing the Vhdl code for XOR gate. Okay. Here also we have entity, architecture and library part. Okay. In this program, XOR 1 is the entity name. Arc is the architecture name. I am taking 2 inputs XOR gate. Here we have 2 inputs XOR gate. So I am writing the program for 2 inputs XOR gate. Okay. A and B are inputs. C is the output. All are single bit. Okay. So entity XOR 1 is. Next I am declaring input output ports of XOR gate. Port, open the bracket, A, B colon. A and B are inputs. So you have to use mode in. A and B are single bit value. So here you have to write STD logic or bit. Semicolon. Next I am declaring output. C colon out. C is the single bit value. So STD logic or bit. C colon out STD logic. Next in the third line you have to write end entity name. So end XOR 1 colon. Next architecture part. In the architecture part, first line will be architecture name of entity name is. In this program, XOR1 is the entity name, arc is the architecture name. So architecture arc of XOR1 is. Next you have to write begin. Next I am defining the logic of the two inputs or XOR gate. Okay, so C less than equal to A XOR B. A is XORed with B, then the result will be stored in the output C. Next, end architecture name is arc. So end arc. Okay. This is the Vhdl code for 4-bit binary adder subtractor in structural model. Okay. First, we see entity part. Okay. In this program, add sub is the entity name, structural is the architecture name. Okay, so add sub is the entity name, structural is the architecture name. In the entity part, first line is entity name is. So entity add sub is. Okay. Next I am declaring input output ports of 4-bit adder subtractor. Okay. You see the diagram here. B3 to B0 is the data B. A3 to A0 is the data A. A and B are inputs. K is also input. S3 to S0 are outputs. C out is the output. Okay. So A comma B colon both are inputs. So you have to use mod n. Next A is 4 bits value. B is also 4 bits value. So here you have to write std logic vector or you can write bit vector 3 down to 0. K is a single bit value. So K colon K is the input. So you have to use in. Then you have to write std logic or bit. Okay. Next C out is the output. It's a single bit value. So C out colon out. Then you have to write std logic or bit. Okay. S3 to S0 are outputs. So S colon out. S is the 4 bits value. So here you have to write std logic vector or bit vector. You can use anyone. Okay. 3 down to 0. In the third line you have to write end entity name. So end add sub. Add sub is the entity name. Okay. Next architecture part. Okay. In the architecture part, first line is architecture name of entity name is. Okay. In this program, add sub is the entity name, structural is the architecture name. So architecture structural of add sub is. Okay. Next, we are writing the program for 4-bit adder subtractor in structural model. Okay. So you have to define the component. In 4-bit adder subtractor we have full adder and XOR gate. Okay. So first I am defining component full adder. Next I am defining the component XOR gate. Okay. The syntax for component is component next component name. Okay. Here component name is full adder. This is the entity name of full adder program. Okay. If you use full adder 1, then here you have to write full adder 1. Okay. So full adder is the entity name of full adder program. Okay. So component name is full adder. Next you have to declare the ports of the full adder. Okay. Here X, Y and Z are inputs, sum and carry are outputs. The same ports should be declared here. Okay, port x comma y comma z colon in std logic colon semicolon sum comma carry colon out std logic. Okay, in the third line you have to write end component. Okay, so first line component name is full adder. This is the entity name of full adder program. Next you have to declare the input output ports of full adder. In the third line you have to write end component. Okay, this is the syntax for component. Next I am defining the component XOR gate. Okay, so component, next you have to write component name. XOR 1 is the entity name of XOR gate program. So here component, next you have to write XOR 1. Okay, you see here port a comma b colon in std logic c colon out std logic. The same ports should be written here. Okay, port a comma b colon in std logic semicolon c colon out std logic. In the third line you have to write end component. Okay, here I am defining full adder. Next I am defining the component XOR gate. Okay, you see the diagram here. B3 to B0 is the binary data B. A3 to A0 is the binary data A. Okay, K is also one of the input. Okay, C out is the output. S3 to S0 are outputs. Here I3 is the output of fourth XOR gate. I2 is the output of third XOR gate. I1 is the output of second XOR gate. I0 is the output of first XOR gate. Okay, I0 is the output of this XOR gate which is applied to the input of full adder. Okay, so I0 act as the input as well as output. The same way I1 is the output of XOR gate but which is input of full adder. Okay, so I3, I2, I1, I0 all are act as input and output. So you have to declare these variables as in out or signal. Okay, if you declare I3 to I0 inside the entity, then you have to use the mode in out, or you can declare inside the architecture, but here you have to use signal, no need to use in out. Okay, signal I3 to I0. So I colon bit vector I is the 4 bits value, so 3 down to 0. Okay, next C0 is the output of first full adder, carry of first full adder which is given to the input of second full adder. Okay, so C0 is the output of full adder 1. The same time C0 is the input of second full adder. Similarly C1 is the output of second full adder but it is the input of third full adder. The same way C2 is the output of third full adder but it is the input of fourth full adder. So C2, C1 and C0 are act as input and output. So you have to declare these variables as in out. Okay, if you declare C2, C1 and C0 inside the entity, then you have to use in out. Okay, or you can declare inside the architecture. Okay, signal C, C2 to C0. So C is the 3 bits value. So C colon bit vector 2 down to 0. Here you can use bit vector or STD logic vector. Okay. Next, begin. So here we have to map all the gates. Here I am using the labels x0, x1, x2 and x3 for XOR gate. Okay. I am using FA0, FA1, FA2 and FA3 for full adders. Okay. These are labels. Okay. So first x0 colon, then you have to use component name XOR1, then port map. We are mapping the ports. So you have to write port map. Okay. First you have to write the label, then colon, next component name, then port map, open the bracket. You see here in XOR1 first I am declaring inputs. Okay, A comma B. Then I am declaring output. Okay, so here also you have to first write the input ports of the binary adder, XOR gate of the binary adder subtractor. Okay, here I am taking XOR gate. Okay, you see the diagram here. In first XOR gate, B0 is the input, K is the input, I0 is the output. Please note it here. In first XOR gate, B0 is the input, K is also one of the input, second input, I0 is the output of first XOR gate of 4-bit adder subtractor. So here you have to write K comma B of 0 comma I of 0. B is declared as vector, so you have to write B of 0. Okay, comma I is also declared as bit vector, so here you have to write I of 0. Okay, K B of 0 or inputs, I of 0 is the output of XOR gate. Okay, next I am calling the first full adder. Okay, in the first full adder, I0, A0, Cin are the inputs, C0 and S0 are outputs. So this is the label for first full adder FA0. Then you have to write colon. Then I am calling the same full adder. So here you have to write full adder port map. In the full adder program, first we are declaring the input ports, then output. Okay. So here K A of 0, comma I of 0, comma S of 0, comma C of 0. Okay. Next I am calling second XOR gate. In the second XOR gate, B1 is the input, K is the input, I1 is the output. Please note it. B1 is the input, K is the second input, I1 is the output. Now X1 is the label for second XOR gate. X1 colon, I am calling the XOR gate XOR1. Then you have to write port map. Then open the bracket. First you have to write the inputs K comma B of 1 comma I of 1. Next I am calling the second full adder. You see here for second full adder, I1, A1 and C0 are inputs, S1 and C1 are outputs. Here FA1 is the label for second full adder. So FA1 colon, I am calling the same full adder port map. First you have to write the input ports, C of 0, comma a of 1, comma I of 1. Next outputs s of 1, comma b of 1. S of 1, comma C of 1. Okay, small c of 1. Okay, correct. Next I am calling the next XOR gate. In the third XOR gate, B2 and K are inputs, I2 is the output. Okay, B2 and K. So writing x2 colon, x2 is the label for third XOR gate, x2 colon. I am calling the same XOR gate, XOR1 port map, K, B2 are input. So K, comma B of 2, comma I of 2. Okay. Next I am calling the next full adder. For the third full adder, I2, A2 and C1 are inputs, C2 and S2 are outputs. So here FA2 colon, I am calling the same full adder. Next you have to write the port map. Then first you have to write input ports. So C of 1, comma A of 2, comma I of 2. Then outputs S of 2, comma C of 2. Next I am calling fourth XOR gate. In fourth XOR gate, B3 and K are inputs, I3 is the output. I3 is the output. Okay. X3 is the label for fourth XOR gate. So X3 colon, I am calling the XOR gate XOR1. Then you have to write port map. Open the bracket. First you have to write the input ports K, comma B of 3, comma then output I of 3. Next I am calling the fourth full adder. Okay. In the fourth full adder, I3, A3 and C2 are inputs, C out and S3 are outputs. FA3 is the label for fourth full adder. So FA3 colon, I am calling the same full adder port map. Next you have to write the input ports C of 2, A of 3, I of 3. Then output ports S of 3, comma C out. So this is the Vhdl program for 4-bit binary adder subtractor in structural model. Okay. Okay, thank you.